Alright, so number one, they're asking me about an exothermic reaction graph. I know that my reaction graphs for endo and exothermic are always going to have two flat lines and a little mountain. So like these first two. Because of that, I can immediately cross out these last two because these have like a dip in them, and I will never ever ever see an exothermic or endothermic reaction like that. So my answer is between these two. Exothermic reactions will always have a negative enthalpy, and the way that I can figure that out is either remember that your product line will always be below the reactant line in an exothermic reaction, making A my answer. Or you can just pretend to put in random points on the graph. So let's say that this one is like 30 and this one is like, I don't know, 15. So then it's products minus reactants. So 15 minus 30 is a negative enthalpy, also exothermic. So an exothermic graph will always have the products below the reactant line, the product line below the reactant line. Endothermic will always have my product line above the reactant line. All right, number two. Look at this enthalpy information. I see that this is negative, therefore this is exothermic. And now I just have to describe the situation. The temperature increases because it is an exothermic process. Okay, well I see that it says exothermic, so I'll keep it in there just for now. Temperature increases because it is an endothermic process? That's not right, because this is negative, and negative enthalpy always means exothermic, so it is not B. Temperature decreases because it is an exothermic. Okay, it says exo, I'll keep it for now. The temperature decreases because it is an endothermic. That is not right. Negative enthalpy always means exothermic, so it is not D. So now I have to pick either A or C. In an exothermic process, I know that the temperature, meaning outside of the system, the surrounding temperature, is going to get hot. Exothermic is hot. Not hat, hot. So the temperature increases because it is an exothermic process. That sounds right. Temperature getting hotter. Temperature decreases because it is an exothermic process. Temperature wouldn't decrease in an exothermic. It would increase because it's getting hot. So my right answer is A. All right, next one. The specific heat of water. Oh, this is an equation one. So I need my formula. Q is equal to M times C times delta T. There's my formula. The specific heat of water is this. So this is my C. You have 36 grams of water, so this is my M that absorb this amount of heat, and this is my Q. Boom. So I have the Q, I have the M, and I have the C, but the question is asking me about delta T, and it's saying which one of these can will work with my formula given all of these different information. So let me plug it in. So I have that Q is equal to 1200 is equal to 36 times 4.18 times delta T. So let's solve for delta T here, just so we know what delta T should be in this case. So I'm going to multiply 36 times 4.18, 36 times 4.18, and that is equal to 150.48. I still have delta T on this side, and I still have 1200 on this side. So because I'm solving for delta T, I have to divide both sides by 150.48. So let me do 150.48. I know this is taking a bit longer than I would want to. 150.48. All right, so 1200 divided by 150.48 is equal to delta T, I'm going to do it right up here. Delta T is equal to approximately 7.97. 7.97. That's approximately equal to 8. So 8 degrees Celsius. All right. So now from our choices, we have to find a delta T that is approximately equal to 8 degrees Celsius. So remember, delta T is equal to final minus initial. Your final temperature minus the initial temperature has to equal 8. So here, we go from 30 to 22. So 22 is my final, 30 is my initial. My delta T here will be equal to negative 8. Delta T on this one, final is 30, initial is 22. 30 minus 22 is 8. 8 minus 0 is 8. 0 minus 8 is negative 8. So out of all of these changes in temperatures, the only ones that actually equal to 8 degrees Celsius, final minus initial, are B and C. These other ones equal to negative 8, and that is not what we found that we needed our delta T to be. All right, let's move on up. Number 4. So number 4 is telling me that a beaker of cold water is sunk into a jar of hot water. So I got cold water beaker, hot water jar. Which graph shows the temperature of the beaker and the jar and how it will change over time? Okay, so let's look at this first one. This one is saying that my water in the beaker is going to, right, I had to make a few changes. So a jar of cold water is sunk into a beaker of hot water, and I didn't make that change. Okay. So a jar of cold water into a beaker of hot water. Which one shows like how the temperature changes over time? So for this question, you have to know that heat transfers from hot to cold. That means that something that is very hot becomes less hot over time. Something that is very cold becomes less cold over time because it is absorbing that heat. All right, so let's look at these individual graphs. So I have that my hot water in the beaker is going to kind of like curve this way, and the cold water is going to get warmer, and then they're all just going to randomly meet here and then just be the same temperature immediately. So this just doesn't make sense. Like, if something is slowly cooling down, it wouldn't like start to cool down and then go wah, cool down. Or like if something is going to heat up, it wouldn't go heat and boom, heat, and then immediately meet in the middle and be the same temperature. Like, this isn't realistic. That does not happen in real life. Let's look at this one. What my water in the beaker who starts off hot gets kind of cold. All right, that makes sense. And here, they meet at the same temperature, and suddenly the water in the beaker gets hot again. That doesn't happen. When you leave water out that is really hot, it doesn't like get cold and then get hot again. It gets cold and colder and colder and colder. So that is not realistic. Then you've got this one where my hot water is becoming less hot over a period of time, and my cold water is becoming less cold over a period of time, and eventually they meet somewhere over here. This seems like a realistic graph that would happen in the real life. Now let's look over here. So this one is saying that my hot water in the beaker, this line of hot water in the beaker, is going to get more and more cold, cold to the point where the other really cold water started. Why would this be the case? Like, why would hot water that you just leave it, there, become super, super cold? That doesn't happen. It doesn't make sense. Your hot water wouldn't get cold to the point of the coldness that you started with. It would just get to room temperature. So the only one that makes sense here is this one. Your hot progressively gets less hot, your cold progressively gets less cold, and they meet somewhere in the middle. And not as sharply as this one where they just randomly went boom, all right, we're the same temperature. No, it's like a gradual same temperature. All right, number 5. Solid A is 30 degrees Celsius and dunked in liquid B at 50 degrees Celsius. So I'm going to say that liquid B is hot and solid A is cold. Not necessarily cold, but colder, you know? So solid A is cold, liquid B is hot. How we know that heat transfers is from hot to cold. So heat is moving from liquid B to solid A. So the question is, how is heat transferred from solid A and liquid B? So let's see. Solid A and liquid B are both absorbing heat. Well, that's not right because one of them is hotter, so one of them has to be releasing heat and the other one absorbing. Sorry, that's my dog. All right, next one. Solid A and liquid B release heat. Well, liquid B would release heat because it's hot, but solid A is colder. Why would that one be releasing heat? That doesn't make sense, so it's not B. Solid A releases heat, liquid B absorbs heat. Remember, the one that releases the heat has to be hot, the one that absorbs the heat has to be cold, since heat moves from hot to cold. So C is saying that solid A is giving out the heat and into liquid B. So that is not correct. The only answer that is left is this one. That is the correct answer. For some reason, it doesn't let me click it. There it is. Oh, nope. It's just frozen. There it is. So solid A absorbs the heat. It's on this side of my arrow. While liquid B, which is hotter, releases the heat. And that makes sense. Liquid B is hot, so it gives off heat to solid A that is cold and absorbs the heat. All right, and that is where I'm going to stop this first part of the review.